Okay, so today I'm going to be meshing a Formula Student wing in 3D. So you may have seen my previous video or video series on performing a 2D Formula Student wing study. This time we're going to level it up into 3D. So a couple of new techniques to learn. Much of the principles are the same. So this is our geometry. This is the 3D wing that we've designed. You can see that it's triple element. We have end plates, just some randomly sized end plates. So this will be the geometry that we're going to be meshing and then later simulating. But today we'll just be covering the meshing process. So I have my workbench file open. So here is my geometry. So just as I did with the 2D study, I have my domain appropriately sized relative to the length of the body or the chord of the wing. And I have my virtual refinement box, which I have concentrated around the wing, and will be performing a body of influence mesh operation just as we did before with the 2D study, just to concentrate the mesh in this region and resolve the fine scale flow features and structures around the wing and the end plate. Again, I took a plane of symmetry as before, but that will be for another video. So the first thing that we're going to do is check that all of our name selections are correct. So I head over to details here. I've already created the name selections, so if we just have a look at them, if I hide this, you can see the wing better. So we've got the end plate there, highlighted, got our symmetry plane. We have our zero shear walls, so just all these boundaries there to simulate infinite boundary conditions. And we have our pressure outlet, so the flow is going in the positive x direction. We have our velocity inlet, and then we have the wing name selection itself, so flap 2, flap 1, and main plane. So that's that all in check. Make sure that these, the main plane, flap 1 and flap 2, make sure we include these in the program controlled inflation because we want boundary layer elements, those prismatic elements, we want them on the surface of our rear wing to capture the boundary layer correctly. So that's all included in that, as you can see. So the first thing we're going to do is alter our global mesh metrics. So we undersizing here. Again, leave the growth rate at 1.2. Here, max size corresponds to the maximum size of elements that we'll see in our domain. So I've got that set to 0.6 meters, which for this problem should be sufficient. So curvature minimum size here. So we want our mesher or the meshing algorithm to capture curvature. And that literally just means, any highly curved geometries will see smaller elements situated on those features to try and get a more uniform mesh sizing. So we have capture curvature set to yes, and I'm just going to set the minimum curvature size to 0.5 millimeter. Normal angle, leave that at 18 degrees as default, that's fine. Capture proximity is pretty self-explanatory. This is going to be affecting the mesh in the regions where we have, surfaces close to each other. Again, it will concentrate the mesh in those regions as you'd want. Again, leave that at default. Number of cells across graph, we'll have that at 5. The default is 3, 5 should be enough. So that's that all in check. That's for our global mesh settings. We're going to close sizing and open quality. And we're going to set smoothing to high, so it's already set to high, which is good. That's what we want. Target skewness is 0.6. I think we'll find that we may be slightly above that. Inflation, so The way we want the meshing algorithm to build our inflation layers is via the first layer thickness option. So we've done our flat plate theory calculations. So based on the Reynolds number of the simulation, the dimensions of the body, and the kinematic viscosity of the air in our domain, we have come on to a first layer height of this value here that you can see, 2.7667 times 10 to the minus 5. And this will ensure that we have the correct Y plus at the walls to properly resolve the boundary layer. Since we won't be using wall functions. So it's just a little calculator again on pointwise. I think I mentioned it in the previous meshing video. Maximum layers is 12, growth rate is 1.2, and we've got layer compression for collision avoidance. You don't really want stair stepping. And then another important setting here is maximum angle 180 degrees. Sometimes when we have, for example, these highly curved geometries here, especially here, the mesh will struggle to adhere to these sort of very small radius edges. So by setting this, the default is 140, we've set it to 180, and that should alleviate that problem. So if you have any problems with an inflation layer struggling around sharp corners like this, try bumping up this maximum angle to 180, and that should help you out. So that's inflation sorted. And then we're going to go finally up here to advanced, and we want the triangle surface mesher here to be advancing front. I find that just tends to give a better, less skewed mesh. So make sure that that's set to advancing front. I think the default is program controlled. So that's everything done here in the global mesh. What I've done is also I've added a body sizing, as I mentioned earlier. So this is our body of influence. So just before, same as before with 2D, nothing different, except for now we've got 3D geometries. The geometry I've selected is the domain. The body of influence is, if I hide the domain, so you can see the body of influence is, there we go, that's it there. That's what I've got it set to. So it's going to set the element size within this body of influence to 10 centimeters, and sorry, 1 centimeter. And that's what we want, just to give us a better, more refined mesh directly around the wing. So that's that done. Again, growth rate 1.2. As I mentioned in the previous video, this growth rate is important because if our mesh is increasing in size too quickly, it can introduce numerical errors in the CFD code. So 1.2 is fine. Next, or finally, we have a face sizing that I've set, and that will be again on the surface of the wing. So if I show you, if I hide this, and then hide this wall here. Oh, apologies, I've clicked the wrong thing. What we want to do is hide this face, not the body. Where is it? There we go, hide face. Okay. Now this will allow me to select, so I've selected all 32 faces. A quick way, instead of selecting each one by one, like so, the best way to do it is to select the box select mode up here. As you can see, make sure you're on faces and just literally select all, apply, and you'll have 32. So that's how many that we have there. So switch that back to single select. So the element sizing on the wing faces I've set to 5 millimeters, and again a growth rate of 1.2. We want to capture curvature again, same as before, I'm going to set this to 0.5 millimeter instead of 0.3 millimeters. Again, proximity 5 cells across a gap. And that's all there is to this particular mesh. With your problem, it may be different. You may require some extra sizing options, but for this specific geometry, this is what allowed us to generate a decent mesh. Yeah, let's go ahead and mesh that. Okay, so we have our finished mesh. Let's go ahead and inspect some of the features of our mesh that we can see. So we've got this, you can see the virtual refinement box there, and you can see how the capture curvature has concentrated the mesh in this highly curved trailing edge, very small radius there. So you can see at the leading and trailing edges how the mesh is concentrated there. We've got our boundary layer elements as well. So there we go. Yeah, that's it. We can generate a a section plane if we like, and have a look. So if I just cut through the section plane, if I just cut through the main plane. Okay, so let's have a look at what we've got. So you can see the end plate there, and we can see the meshes the inflation layers have followed nicely the curve of the end plate. The elements are smaller around in the immediate vicinity of the end plate. Sorry. Oh, what have we done there? There we go. Let's zoom back in. We've got our prismatic elements to capture the boundary layer there. So it's all looking good. We can go ahead and move to the next step. So yeah, that's all for today. I hope this video was helpful, and